talk about a refrigerant, HC refrigerant performance in the Emirates air-cooled chillers. Dr. Armstrong is an associate professor in mechanical engineering at Masdar Institute. He holds a PhD in building technology from the MIT and an MS in mechanical engineering from Colorado State University. He is experienced in research and application of many new end-use and combined heat and power technologies. He's a member of the ASHRAE or various ASHRAE committees, as well as recipient of different awards relevant to the field. Dr. Armstrong, the floor is yours. Thank you.
Thank you, Bernard. I perhaps, on reviewing the program, would have placed this presentation in the previous session. Actually, our work was originally motivated by the potential for minimum energy performance standards. This work is sponsored by Executive Affairs Authority. And let's see what I do here. Next. Okay. So in the interest of saving time, I have several slides on motivation. I'm going to go through quickly or skip some of them. But I think that the important thing to consider here is that the replacement of refrigerants for reduced ozone depletion should go hand in hand with minimum energy performance standards. That's an opportunity to work through these problems at the same time. Okay, just briefly some motivation in UAE, average per capita energy use in buildings, about 3 kW per capita. This I'm going to return to a couple times in the talk. We did analysis on two different data sets of seasonal variation in energy use, data from ADWEA primarily. And this shows that, see if we can use our pointer. This is 1 year, I believe this is 2010, of electrical energy use. And it shows that the use for cooling is over 50% on an annual basis, over 70% on a peak day basis. And we also looked at attributing the cooling energy to the different drivers. And so we see that solar gains represent less than 20%. That was a bit of a surprise to us. The temperature is over 60%, but humidity is on the order of 20%. And that tells us that the leakiness of buildings and the ventilation, air conditioning constitute a large fraction of the total cooling. In fact, more like 30%, because of course the ventilation air has to be cooled as well as dehumidified. And we'll return to that point a little bit later. Of course, one of the challenges to establish performance standards and building codes is a long history of low energy costs in UAE. And so there's not a great deal of, shall we say, technical and business presence in energy efficiency. Of course, that's changing rather rapidly, fortunately. Again, to highlight the lack of incentive, UAE, we'll go back. Can we go backwards or not? Okay, thank you. Energy prices in Abu Dhabi, about 4.5 cents per kilowatt hour. In developed countries that have less subsidies, but well, in the case of Canada, good resources, we're up to 8 cents. US and France, around 12 cents. UK, around 18 cents. And Japan, over 20 cents per kilowatt hour. So I would just to offer an opinion, hand in hand with the minimum energy performance standards, we really need to do something about rate reform to turn around the industry in this country. Where should I point it? Okay. Let's skip this. I want to get to what we've actually been doing. Okay, so our program has been to develop optimized designs for packaged chiller equipment in the 500 to 1,000 kilowatt capacity range. And I think we've learned over the years that simply modeling a piece of technology is not going to produce a very credible answer. So what we do is develop the models, component-based models that are very flexible. We can drop in different compressors, different size of evaporators and condensers, variable speed compressors, condenser fans, various kinds of controls. And to get some credibility, we have a baseline chiller that we monitor and validate the component models that we've developed. And I'll just go through a few shots. One of the most difficult things to measure in the field is the condenser airflow rate. So here we have a fan-assisted flow meter calibrated, and it sits on top of, this is for a single condenser fan. I believe it's about 60 cubic meters. Well, I have the number, around 30 cubic meters per second. And we actually do redundant measurements, so we measure the flow of each condenser fan with this apparatus, which has been calibrated using the ASME nozzle apparatus. And then we also do traverses, and here you see a screen that shields the condenser inlet face from the wind so as not to bias the measurements. And with these two methods, we can get agreement to about 5%. And that helps us to get a heat balance on the whole machine to about 5%. Just some other measurements and some surprises. Generally, we measure refrigerant conditions with plugging pressure transducers directly into service ports, measuring suction and discharge pipe surface temperatures, which works rather well if it's done properly. But some other things are challenging. So we found that oh my goodness. That the temperature distribution on the condenser discharge is not what we'd like to assume, which is uniform, and therefore we have to have distributed arrays of thermocouples to measure the temperature rise through the condenser on the air side accurately. Similarly, on the water side, there's quite a bit of stratification in the chilled water supply line, so we had to deal with that. So just move back. Now let me return to the modeling. The evaporator and condenser can be modeled quite accurately based on engineering principles. We use effectiveness NTU models with a moving phase boundary. And these we're able to validate from the measured data. The compressor is another story, and in particular on this machine, we have an economized screw compressor. And our initial efforts have been to operate the machine over a wide range of conditions. This is a variable speed screw compressor, runs from about 40 to 200 hertz shaft speed. And each compressor has two models. The volumetric efficiency is fairly flat. The isentropic efficiency, this is typical of a screw compressor. It drops operating above its optimal pressure ratio, and it drops rather rapidly below the design pressure ratio. On the right-hand side, you have similar models. And it's interesting to contrast the two. So the volumetric efficiency is dropping with frequency on the screw compressor, primarily due to back leakage. It's rising with the reciprocating compressor due to reduced flow friction losses. And even more important is the isentropic efficiency, which is quite flat with pressure ratio for the reciprocating compressor. So we'll come back to that a little bit later. Now, from this collection of components, condenser, evaporator, throttling device, and compressor, we can, and of course the refrigerant properties have to be evaluated. And at any given condition, we can determine the chiller COP, or I'm going to speak in terms of specific power, so 1 over COP. And what we end up doing is running the model at a wide range of conditions. Here we have capacity fraction in tenths from 0.2 to 1, outdoor ambient, and you'll have to forgive me, we went as high as 45 C, and I think we'll go back and raise it a little higher. And I'll return to that in a moment. And then evaporating temperatures from -1 to 5 C. So just very quickly, here's the magenta is for 45 C. The cayenne is for, I can't remember, 40. Red is 35. Green is 30, and blue is 25. So we see the specific power, as you expect, rises with capacity fraction with a variable speed compressor, starting from a rather low capacity fraction of about 0.3. But below 0.3, again, performance starts to drop because we have a certain overhead with the inverter and some of the flow back leakage losses in the compressor. And of course, the specific power increases rapidly with pressure ratio, so for the higher ambient temperatures. So we have, I think, 4 by 5, 160 points here, to which we fit a modified tricubic equation. It's modified in that we often have to use a higher order relationship for the capacity fraction to be accurate. We try and get RMS on the order of 0.5% for these curve fits. So we have a very physically based model that takes a long time to execute, particularly when we're trying to optimize the coordination of fan and compressor speeds during the solution, and other things that we can optimize like subcooling. But in the end, fitting a performance map to these points, we can plug into a simulation program and execute a year's worth of operation in a few seconds. Okay, so what do we get out of all this? Oh, sorry, I want to illustrate the, for example, the subcooling control. Here you can see that the specific power at the full capacity high pressure ratio is about 10% less with the optimal subcooling than without. Okay, so the idea of finding optimal designs to establish minimum energy performance standards is not to tell a manufacturer how to build a machine. The idea is to test a wide variety of designs that come close to reaching least life cycle cost in a particular climate with a particular refrigerant, and to demonstrate that there are a variety of designs that can meet a target standard, and really to find out what that target standard should be. So here's some list of some of the features, design features that we try in a variety of combinations. Some play together well, better than others. Let's see, I don't know if I can read them from here. Compressor and evaporator size obviously is an important feature. variable frequency drives for compressors, fans, and pumps. Advanced cycles, we've modeled, actually we haven't modeled an expander, but ejector cycle. We will be modeling liquid vapor heat exchanger, and as I mentioned before, subcooling control. Flash cooling of the discharge vapor, two-stage and economized compressors, various kinds of intercooling, different compressor types, different refrigerants, and in this next week or so, actually, we'll be modeling machines with evaporatively cooled condensers, which can give us a higher performance increase than we could get with a conventional cooling tower chiller combination using the same amount of water. Let's see. Okay, so this is, as I say, this is a work in progress. This is the template for life cycle cost analysis. Probably familiar, something similar to this to most of you. Okay. Oh, there's a monitor. It's too bad my eyesight can't read it from here. If someone can recommend a good cataract surgeon, I'll be listening. So our metric for comparison of different designs is the net present value, and you just see the various factors. This table is for the cost numbers or for the baseline chiller with variable speed fans. So it's the next notch above the baseline chiller. And we simply add up the component. Oh, and by the way, it's not mentioned here, it's for a 12 cent per kilowatt hour flat rate. And there should be a sum at the bottom here of about, well, notice that for a chiller close to the baseline chiller, relatively low cost, $137,000. The electric cost present value over a 20-year analysis period is over $1 million. Okay, I'm getting the sign. Let's just quickly look at what happens here. The most notable thing we found for all the combinations of controls and different compressors is that the condenser and evaporator size comes out, optimal size comes out to be about 1.5 times what the baseline is. So clearly there's room for improvement. Just to quickly read off some numbers, we have SEER improvements of about 20% for just the oversized condenser, further improvements for optimal subcooling of about I think it's 10%, and variable speed fans take us further. But the real improvements are when we go from the screw compressor to the reciprocating compressor, where we get SEER improvements of up to about 70%. Finally, we did just a few runs recently with different refrigerants, one of them being butane, showing SEER improvement of just over 1%, and ammonia showing SEER improvement of over 13%. So